Hello everybody and welcome to this lecture on spectral line interferometry. My name is James Allison and I'm a researcher here at the University of Oxford. And although I'm giving this lecture, I should give my thanks to Jack Radcliffe, who prepared much of the material that you're going to see here in these slides. So this lecture is split into two parts. The first part focuses on the science that you can do with spectral lines, and the second part focuses on the analysis and data reduction of spectral line interferometric data. So in the first part, we're going to talk about what spectral lines actually are physically and how they can be used to determine the physical and chemical conditions of objects in the universe. In the second part, we're going to talk more about the differences between how you actually do observations in spectral line versus in the continuum, how you set up your spectral line observations, and how you do the reduction of the data and analyze the data for science. Looking at the science of spectral lines, one question you might ask yourself is, what is the key reason why we study spectral lines as opposed to just the continuum emission from radio sources? So at the wavelength, at radio and millimeter wavelengths, spectral lines are very important for studying the material, the interstellar medium between stars in galaxies. Now, the interstellar medium itself comprises a vast range of different physical and chemical conditions. It is not in thermal equilibrium with itself, so there is a huge range of different temperatures and densities across on all different scales. And spectral lines tell you about the different conditions, the different physical conditions at positions within the interstellar medium. And it also tells you, of course, because spectral lines are unique, their rest frequencies are unique to specific elements or so atoms and molecules, that tells you something about the chemical abundances of these different atoms and molecules in a particular region of space. So they act as a way of being able to determine what the chemical composition is, as well as the physical conditions of a given region of space. Not only that, they're very useful because they occur at a specific rest frequency. It means that if they are shifted from that rest frequency due to the Doppler effect, which we'll talk about in a bit, it means that we can determine the dynamics of the gas that's going on, that's emitting or absorbing that spectral line. And that means we can also determine the sort of global physical properties, such as the kinematics of the gas, which allows us to understand not only about things like the turbulent motion of the gas in the interstellar medium, but also its bulk rotation, which tells us something about the dynamical mass of the galaxy that we're looking at. So there are a lot of ways in which we can use spectral lines for science, which are very important. Now, the science in this lecture is going to focus heavily on molecular clouds in the Milky Way galaxy, and there's a reason for that, because molecular clouds comprise a huge richness of different elements and atoms and molecules. Now, molecular clouds comprise, as they sound, mostly of molecular hydrogen. They're cold at about 10 Kelvin. The hydrogen forms molecules. And in addition to that, we have helium, which is in its primordial abundance with hydrogen at about 25%. And then at much lower abundances, we have dust. Now, dust is very important. It's a very important component of the interstellar medium because it's used both as a way of protecting the molecular cloud from the background ultraviolet radiation, but as well as being very important as a source of heating in the interstellar medium. In addition to that, we have carbon monoxide, the carbon monoxide molecule at lower abundances. Now, carbon monoxide, even though it's a small fraction of the total molecular gas, is a very important molecule astronomically because we use it as a way of being able to trace the molecular clouds in galaxies. And that's because H2, molecular hydrogen, is not detectable at radio wavelengths. And so we need to use the carbon monoxide lines in order to be able to trace the molecular gas in galaxies. And in addition to that, in a molecular cloud, we have many other atoms and molecules, which I'll show you soon, at much lower abundances. An example of a molecular cloud is this beautiful Orion Kleiman-Lowell nebula that we see here. Now, a survey was undertaken of this region, the star-forming region, using the IRAM 30-meter telescope at 100 gigahertz. And that's to detect the molecular gas that's associated in the cloud with this region of star formation. Now, 100 gigahertz is important because that's roughly the frequencies where we expect to detect many molecular spectral lines. So let's see what one of these spectra looks like from those observations. And that's what we have here. So we have the spectrum here, which shows frequency on the x-axis and antenna temperature on the y-axis. And you can see that there are a lot of spectral lines here. And each of these spectral lines corresponds to a transition in a given molecule. And you can see that there are quite complicated molecules here. Hydrocarbons that comprise, obviously, carbon and hydrogen, and then you have nitrogen, oxygen, silicon, and other elements embedded in this molecular cloud. And what we see in these three different panels is basically a zoom in. So you start off at a lower looking at the brightest lines at the top panel there, and then as you go sort of zoom in on the what's called the spectral baseline, so that's at sort of the bottom of the spectrum, you start to see other spectral lines pop out at higher resolution, and as we eventually get to the bottom of the spectrum, you can see that there are lots of spectral lines there that aren't even identified. And in fact, we get to the point actually where this spectrum is confused. There are so many spectral lines that we can't distinguish between the lines at the spectral baseline here, which is actually incredible when you think about it. And it really shows how many different molecules, how many different transitions even that we can detect in this one molecular cloud. Each of those spectral lines that we saw there at a particular frequency corresponded to a particular transition of a particular molecule. And what I mean is that the molecule these are emission lines, so the molecule has undergone a decay from a higher energy state to a lower energy state. And in doing so, it has emitted photons of a fixed quantized amount of energy and therefore correspondingly a fixed rest frequency. Now, the processes that can generate either the emission or the absorption of a photon are as follows. We have spontaneous emission. So spontaneous emission occurs because a given molecule is in a higher energy state, and it just, with some probability, randomly emits a photon. And the rate at which that occurs depends, of course, on how many of that molecule are actually in the upper state to begin with, which depends on the excitation temperature of the gas that we're considering. But it also depends on fundamentally the probability of that transition occurring. And that's parameterized by what's called the Einstein A coefficient. Now, in addition to that, that sort of random emission that occurs in isolation, essentially, the molecules and atoms can also absorb and emit photons through interaction with the background radiation field. So absorption occurs exactly as it sounds. An incident photon from the background radiation field will be of the right energy will be absorbed and excite the molecule from a lower state to an upper state. And in addition to that, we have what's called stimulated emission. And stimulated emission is where an incident photon actually stimulates the emission of an additional photon and the decay of the molecule to a lower energy state. And in both cases, of course, that depends, those processes, the absorption and stimulated emission, depend on the density of the background radiation field. And they also have their own rate constants, which are given by the Einstein B coefficients. Now, as a science student, probably the first thing that comes to your mind when you think about the emission or absorption of photons is the transition of electrons in the energy states of an atom, so in the orbital energy states of an atom. Now, obviously, the orbital energy states of an atom depend on the nucleus, on the chemistry of that particular atom, the element that it corresponds to. And so when we look at the spectral lines that correspond to all the different transitions in the orbital states, that tells us that's essentially a fingerprint for that species. Okay. Now, here we have an example which is just the hydrogen atom. Now, the hydrogen, as I've said, forms the majority of baryonic matter in the universe. It's the most common element throughout the universe. And so it's a very important element to study, even though it's very simple. And what we can see here are the number of the energy states. So we have the n orbital states from numbered 1 upwards in number. And we see here the different wavelengths that different transitions correspond to between between the different energy states, the wavelengths of the photons that are emitted. And what you can see here is these all seem to be in nanometers. So unfortunately for us radio astronomers who are used to dealing more in centimeters, millimeters, and even meters, these transitions are far too short wavelength. In fact, they're the optical and the ultraviolet end of the spectrum. So we wouldn't be able to detect the electron transitions in a hydrogen atom. But in the optical you can, in the UV you can. And these different series correspond to different transitions between the different orbital states. And one of the most common lines that we observe in the optical is what's called the H-alpha line. Now the H-alpha line, which corresponds to the n equals 3 to n equals 2 transition, it's part of what's called the Balmer series. This is important because this is most likely generated because what happens is your electron starts off in an excited state in the atom because you have essentially hydrogen ions, you have ionized hydrogen, which obviously are just protons, and those protons capture electrons that are in the same space. Right, and once they capture that electron then essentially sort of cascades down through the energy states, producing emission lines. And one of those emission lines is the H-alpha line. So the H-alpha line is a tracer for the ionized hydrogen in the universe, in galaxies in the universe. And that's really important because it corresponds to that gas is ionized by the background photons. And so those photons, those high energy photons that are ionizing the gas, correspond to ongoing massive star formation. And so H-alpha is a very good indicator. The ionized gas is a very good tracer of where star formation is occurring. And so we can see that, for example, in this survey of the Milky Way plane in the optical, which shows, so we have here in galactic coordinates, so we have the Milky Way plane here along the equator, and then the galactic poles are north and south here. And so you can see there are these regions of ionized gas that have been ionized by massive star formation. And now, unfortunately, in the radio, as I said, we can't detect this. What we see in the radio are these H2 regions, so these ionized hydrogen regions, where continuum emission is generated by the ionized gas. But we can't see this in the spectral lines. So, what sort of spectral lines can we detect in the radio in the centimeter and millimeter wavelength regimes? Well, one of the most common spectral lines observed in radio astronomy is the 21 centimeter line, which of course is actually the line that occurs at 21 centimeters wavelength, which corresponds to about 1400 megahertz in frequency. And this line is associated with a transition in atomic hydrogen, neutral atomic hydrogen. So we have a single hydrogen atom, we have a proton, and it's got an electron, and this electron is in the ground state. Now the proton and the electron have a spin associated with them. And through the rules of quantum mechanics, those spins interact with each other, and those spins can either be aligned or they can be anti-aligned, anti-parallel. And in the aligned state, that requires more energy than in the anti-aligned state. And so it can absorb or emit a photon of a fixed energy corresponding to 1400 megahertz or 21 centimeters that drives that transition. Now, that transition is actually forbidden by the quantum selection rules. So it means the probability of that transition occurring, is very, very small. It takes about 10 million years for a single atom to actually undergo that transition on average. However, because we have so much hydrogen in the universe, it's the most abundant element, as I've already said, and there are a lot of hydrogen atoms even in the Milky Way galaxy. We actually detect the 21 centimeter line quite regularly, and in fact, it was detected very early on in radio astronomy in 1951. And this was actually this was the birth of spectral line radio astronomy. It was the first transition detected, and it's been very important ever since for many different applications of science, both in the interstellar medium and in galaxies in the distant universe. So previously I showed you that wonderful spectrum from the Orion-Kleiman Low Nebula, which had all these different spectral lines associated with different molecules, different complex molecules in the molecular gas in that cloud. Now, as I mentioned, those observations were undertaken with the IRAM 30-meter telescope at 100 gigahertz. Now, the question then is, where do those spectral lines come from? Because as I've already mentioned, the spectral lines associated with the different orbitals of an atom, the electronic transitions associated with the orbitals of an atom, occur at much shorter wavelengths than the radio. They occur in the visible and ultraviolet bands. So what is this longer wavelength? Where are these longer wavelength spectral lines coming from? Well, molecules themselves have other transitional states that occur. So they have rotational and vibrational states, as you can see here, from the interaction between the bonded electrons and the nuclei in the molecule. and they have both these rotational and vibrational states. And the rotational states typically occur when there's a dipole, so when there's a separation of charge, such that when you get a rotation, you get a interaction between the distribution of charge with the background electromagnetic field. And that occurs at the sort of millimeter wavelengths, so the 100 gigahertz wavelengths that we were seeing there. And then at shorter wavelengths, at higher frequencies in the infrared, we get many of the vibrational transitions of molecules. And then, of course, at the very shortest wavelengths, at the highest frequencies, we get the orbital transitions of the electrons. And so what we see here is the potential energy associated with a diatomic molecule, which kind of nicely shows us as a schematic what's going on with these different transitions. So on the x-axis here, we have the separation. So this is a diatomic molecule, so it's a two-atom molecule. And we have the separation here between the nuclei of the two atoms. And so we have a distance RE, which is the equilibrium distance. So as those two nuclei get close to each other, you get a repulsive force, and as they get stretched apart from each other, you get an attraction force, and there's an equilibrium position. And then the vibrational states and the rotational states are quantized, and that's what we're seeing here with these different energy levels. And in addition to that, we also have the quantization of the electron states as well, the actual orbital states. And so we have here a diagram showing all of those different states and colored. So we have, for example, the green transition that's shown here is a transition from one rotational state to another, from the ground state to another. And you can see that is the lowest energy, so the longest wavelength state. And that occurs in sort of the sub-millimeter regime, which is really what we're detecting with these interferometers like ALMA or with this single dish IRAM 30-meter telescope. And then when we go to transitions between the different vibrational states, we're going to shorter wavelengths, and that's associated with infrared. So that's spectral lines that we might detect in the infrared with an infrared telescope. And then finally, when we go to the electronic states, so the different quantized states of the orbits of the electrons, that's when we're in the visible and UV domain. So this gives you a really nice idea about what the different wavelengths are. Now, of course, in the radio band, what we're most interested in with the molecules, observing molecules, is of course the rotational transitions. Now, moving away from how spectral lines are generated physically and looking a little bit more about how they're used to measure properties of astrophysical media, which we're interested in studying, one of the key concepts here is called the optical depth. Now, the optical depth is equal to the integral of what's called the absorptivity. The absorptivity is an intrinsic property of the medium at that frequency, at that wavelength that is related to the transition. And that is then, if you integrate that over the medium, the thickness of the medium that you have, then you get what's called the optical depth, which is effectively a measure of how much the incident radiation is absorbed or scattered. Now, in terms of how that then relates to the line strength, so if you consider an emission line, so an emission line is being generated by the medium itself. It's related to the excitation temperature of that medium. So how many of the molecule or atom are in the upper state, the upper energy state, to generate the radiation that you're detecting, which I've labeled B here. Now B is effectively the expected intensity of radiation depending on that excitation temperature. And that is then, of course, attenuated by absorption and scattering processes along the line of sight through the medium. So it depends then on the optical depth. So that's what you get, that relationship there between IE, which is the detected emission line, and B, which is the emitted intensity at that frequency. And what's important to notice there is if you have an optically thin medium, you see that approximately that then becomes just the product of B and tau. So what that means is that when you measure your emission line, it depends both on the intrinsic properties of the emission, but also on the thickness of medium that you have. However, as you go to larger optical depths and the object goes from being what's called optically thin to optically thick, that basically means that tau goes from being much less than 1 to being much greater than 1. You notice then that the dependence on tau disappears, and you end up with effectively just your emission line then just depends on the sort of shell around the object that you're studying. And so these are very important in astrophysics. These are the differences between an optically thin and optically thick medium when you're looking at an emission line. Then being able to relate that back to things like the mass of the molecular cloud, or the number of atoms along the line of sight, obviously that becomes important because you no longer get, in the optically thick case, you no longer really get a measurement of the number of atoms along the line of sight because your cloud is now optically thick, so you can't measure that. In the case of the absorption line, so the absorption line is relatively simple. You have an incident radiation source, such as a background radio source, for example, an extragalactic source coming through the galaxy, and we detect an absorption line from some intervening gas, either a molecular cloud or some hydrogen gas along the line of sight. And so you measure an absorption line there, and it's just the fraction of incident radiation is then absorbed, and that allows you to then determine the optical depth, which then allows you to determine things such as the number density of atoms along the sight, the column density of atoms and molecules along the line of sight towards your background source, and other things such as its temperature. In addition to the line strength, which tells us about the amount of stuff, the amount of medium between us and the incident radiation source, we can also use the line profile. So we can use the fact that lines are observed to have a finite width. Now, you might wonder why that is, because, as I said before, spectral line is associated with a fixed frequency. It's associated with a given set of photons at a given energy, and so why would you then expect to see some sort of range of frequencies in your spectral line? Well, that's because, of course, there are other physical processes going on that lead to the broadening of spectral lines. So the most fundamental one would be what's called natural broadening, and natural broadening occurs because your spectral line has a probability. So an emission line, a spontaneous emission, for example, has a time scale associated with it. As I said before, 21 centimeter line emission occurs. The expectation value for that is about 10 million years, and so there is a sort of finite time scale associated with a spectral line happening, with a transition associated with the spectral line happening. And so that then leads to, through the uncertainty principle, through Heisenberg's uncertainty principle, leads to a finite range of energies that photons are emitted or absorbed at, and therefore leads to a finite range of frequencies that we observe that spectral line at. Now, in the case of the 21 centimeter emission line, the time scale involved is very large, which corresponds to a very narrow range of frequencies over which natural broadening occurs for the 21 centimeter line. So it ends up being a very useful transition in order to measure very precisely the frequencies and then associated other processes such as Doppler shift with that line. In addition to broadening through natural broadening, we also have what's called thermal Doppler broadening. So Doppler shift, which I'll get onto in the next few slides, through the random motion, basically atoms and molecules have finite temperatures, right? They're not at 0 Kelvin. They have a finite temperature associated with them, and so they will then have random motion through just kinetic theory associated with that temperature. So they'll have a line of sight velocity, random velocity, which will then lead to broadening of the line through the Doppler shift. And that's because basically we have red shifting and blue shifting of the light, the radio light that we're detecting, that leads to a broadening of the line. Then in addition to that, we also have what's called collisional broadening. So that occurs because effectively collisions between the molecules and atoms and other particles in the gas will lead to a shortening of the time scale associated with that transition. And so that will lead to, through, again, the Heisenberg uncertainty principle, will lead to a smaller delta t and therefore a larger delta E, which leads to a wider line width. And there are other processes as well. So one example is Zeeman splitting. Zeeman splitting is the fact that the atoms and molecules can interact with strong magnetic fields, ambient magnetic fields, which will lead to further splitting of the transition, the two levels, the energy levels between which this transition is occurring, that's generating the spectral line, and that will lead to splitting of the line and what appears to be broadening, of course, because of that. Now, one of the other processes which I'm about to get onto as well is the fact that, as I've mentioned, through thermal Doppler broadening, there is this Doppler effect of the fact that atoms and molecules can be moving away or towards us. Now, if you have if you have an observation where your gas actually turns out that the bulk motion of your gas is not just at one velocity, but, for example, if you have a rotating galaxy, then if you can't resolve that with your telescope, so if your galaxy is, say, very far away, then the spectral line that you detect is just going to be an average sort of a profile over all the gas that's moving at different velocities. And so that will lead to a very broad line width, much wider than the natural broadening width or even the thermal Doppler broadening width. So that's another sort of line broadening mechanism, is just bulk motion of the gas itself. So let's explore Doppler shift a little bit more then in the context of spectral lines. So probably the most common analogy that you would have heard about the effect of Doppler shift is through sound. So if you're stood by, for example, by the roadside and you hear an approaching emergency vehicle with its siren on, then as it approaches you, you'll hear the pitch rising, okay, as it's approaching. And basically what that means is that the sound is going to shorter wavelengths. Okay, so the frequency is increasing. And then as it moves away from you, that pitch then becomes lower and the wavelengths increase. The wavelength of the emitted sound increases and the frequency gets lower. And so what you have there is an example of what's called Doppler shift. Now, with electromagnetic waves and with photons, of course, that's seen in terms of the frequency and the wavelength that you observe. So a source, an object that is emitting radiation that is moving towards you, it's going to be shifted. The wavelengths of the light that you detect is going to be shifted to the blue end of the spectrum, and then as that object moves away from you, it gets shifted to the red end of the spectrum. And so that's obviously in radio astronomy, we would measure that as a radio frequency. Now, what's interesting, there are lots of different applications of this, of course, in astrophysics and astronomy. We're sort of focusing a lot on the Milky Way in this lecture. Now, the Milky Way. What's interesting is we're inside the galactic plane, of course. We're located, it's indicated here in this diagram. You can see that we're located where the sun is. They're about 8 kiloparsecs from the galactic center. Now, the Milky Way has what's called differential rotation. And so that means that we actually then see Doppler shift associated with objects that we see either away from the galactic center or towards the galactic center with respect to us. And so an object that is sort of in the inner orbit is moving faster than an object that's in the outer orbit. And that means then that if we look, for example, towards the direction of rotation of the Milky Way as indicated in this diagram, then objects that are in the inner orbit, and inner orbit with respect to us, are pulling away from us. And so we're going to see, in terms of a radial velocity with respect to us, we're going to see that object's light is redshifted, right? But then if we now look at an object that is further away, at a higher orbit, a larger orbit, that's actually sort of lagging with respect to us. And so that means then that if we look towards the direction of rotation, it's going to be blue shifted because we're sort of catching up with it. Okay, and so that's what you see in the Milky Way, and that's a really important application of Doppler shift, because we can actually use that, as I'll get onto later, to do things like measure the distribution of gas in the Milky Way galaxy. Right, now that's the sort of the overall what's going on here. But how do you actually then use that shift? How do you use that measured shift to measure the velocity? So the way you do that is you know what your rest frequency or rest wavelength of your spectral line is, okay, which is given in this equation here by lambda true. And equally, you could do this in terms of frequency, and then it would be given by frequency true. And you know what you then observe your line at a given shifted frequency, right, or wavelength, and that's your lambda observed. And then you use this equation here to then measure the relative velocity between us and the object, the gas that's absorbing or emitting that you're studying. And so we then can use that to look at the kinematics of the gas. So if the gas is moving at lots of different velocities, then we see lots of different shifts in different directions, and we can start to map out the velocity distribution of the gas. So not only where it is in the sky, but actually where it is kinematically in the sky. And that can tell us, I'll get onto this in a minute, but this can tell us, for example, what the radial distribution is of the gas. I'm just going to show you a few videos now that nicely demonstrate this idea of Doppler shift and how we use it. So here we have a picture of a galaxy, as you can see, and it looks pretty similar to our own galaxy, in fact. And imagine that you're the observer towards basically where the direction of those arrows is pointing. And what we've got here is we've got the emitted spectrum, which you can see is just given by these nice bands here of color, and you can see there are some absorption lines in that spectrum. And so those absorption lines there, probably from gas that's in this galaxy, seen against the stellar continuum of this galaxy. And so what I'm going to do is I'm going to press play on here, and you're going to see the galaxy is rotating. Okay, and it's rotating in such a way, such an orientation that means that on the left-hand side you can see that gas that's moving towards gas that's on the left-hand side is moving towards us, and gas that's on the right-hand side is moving away from us. And so that generates, then you can see a shift in the absorption lines. So on the left-hand side they're shifted bluewards, and on the right-hand side they're shifted redwards, as you'd expect. And in the center, they're in the rest, because there's only tangential motion at that point with respect to our sight line, and there's no radial motion, so we don't see any Doppler shift there. So that's kind of how we use this, and this would allow us, of course, for this galaxy, which we actually can measure the spatial distribution of the gas and measure individual spectra for positions across the galaxy. This then allows us to map out kinematically the gas in this galaxy, which is very important, not only in our own galaxy, but for extragalactic science, and in fact has been used for measuring things like the total enclosed mass of the galaxy, and therefore inferring the dark matter content. So measuring a rotation curve for the galaxy and actually inferring that there must be dark matter there is a very important concept in astrophysics. And here's another nice demonstration, which is from 21 centimeter line emission from neutral hydrogen gas in our own Milky Way galaxy. So what you see here on this image, we've got here a coordinate system that is based on galactic coordinates, which means that the galactic poles are in the north-south position, and the galactic plane is along the equator in this diagram. And the galactic center is right towards the center of this plot. Okay, and so what we're seeing here is we're seeing emission from 21 centimeter line emission from neutral atomic hydrogen in the Milky Way galaxy. And what we're doing is we're stepping through, so in this video, I'll just play it again, is we're stepping through different velocity channels within which 21 centimeter line is being measured. And so what you'll see that emission starts to pop up on the left-hand side of this plot first, and that's because, as I mentioned before, and then you see it disappears away again onto the right-hand side as we go from negative velocities to positive velocities, i.e. from blue shift to red shift. And that's because, as I mentioned before, when we're looking towards inner orbits, towards the galactic center, what we're seeing is we're going to be seeing gas that is moving faster. It's actually moving, with respect to us, it's basically going to be, if we're looking away from the galactic rotation, we're going to see gas that's catching up with us. And then as we look away from the galactic rotation on the right-hand side, we're going to see gas that's moving away from us. And so that's why we see this. We see this blue and then red shift as we go from left to right. And that's because there's a lot of H1 gas in the inner orbit of our Milky Way that we can detect. But you'll also see as well some gas that's associated with the outer orbit as well there, but it won't be as strong. And what we can actually use with that information from that video that I just showed about how the H1 gas that we detect in 21 centimeter line emission is distributed kinematically in our Milky Way galaxy is we can actually use that additional velocity information in addition to the spatial information that we have on the sky in order to be able to reconstruct the radial distance of the gas that we're detecting, because the velocity maps to, because of this differential rotation, we can actually construct a model of what the rotation of the Milky Way should be, and therefore we can actually map H1 gas that we detect to specific positions in the Milky Way galaxy. So we get a measure of what's called the kinematic distance to the H1 gas that we're detecting there. And that's really important because that tells us about the distribution of H1 gas in our Milky Way galaxy. And H1 is very important because it is a reservoir for neutral gas in our galaxy, which is important for things like future star formation, as well as being used in absorption for measuring the distance to background sources as well, such as H2 regions, supernova remnants, and things like radio loud X-ray binaries as well, and pulsars. So there are lots of applications for this kinematic distance measurement. Now, one of the downsides to kinematic measurement distances is what's called the near-far degeneracy. So within the solar circle, what I mean there is within 8 kiloparsecs of the galactic center, so within our orbit, you actually find that the kinematic distance that you infer, basically because as the gas is moving round, it has a velocity with respect to us, and as it goes back round the far side, it has the same radial velocity with respect to us. And so we get a near-far degeneracy. And so this is not a perfect way of measuring distances for that reason. That is an additional complication. But we can find ways of being able to at least infer what the distance of the gas or the object is based on this technique. So far, when I've been talking about spectral lines, I've been focusing, of course, on spectral line emission and absorption mechanisms, as well as talking a little bit about how dust is important because it does things like heat up gas through thermal emission, when I was talking about molecular clouds towards the beginning of this lecture. But there are some other emission processes in astrophysics which we should briefly discuss, which are important and related to the sorts of science that spectral lines are used for. So I'm just going to talk about those now. So you can see here there are three, and we're just going to go into them into a bit more detail. So the first is what's called maser emission. Now, maser emission is very important in spectral line science because it's effectively a molecular version of what's called a laser. You may have heard of a laser, of course, before. Almost certainly have. Now, a maser is effectively stimulated emission. So I've already talked about stimulated emission already. So the idea there is you have some atom or molecule that's in an upper state, and it emits a photon due to interaction with an incident second photon. Now, the key difference here between sort of normal stimulated emission associated with a thermal population is that in maser emission, it's a non-thermal population. And that's because what's happened is there's been a secondary process, a pumping mechanism, that has effectively moved a significant fraction of the atom or molecule to the upper level associated with this transition through either some sort of incident continuum emission that's moved it up to higher energy levels of this atom or molecule, which is then sort of cascaded down to the upper level. And so what that ends up doing is that ends up essentially multiplying when you have the incident photons coming through of a fixed wavelength through this medium. You end up with many more of photons at that same wavelength, and you end up with a potentially very strong emission line from this maser transition. There are other emission processes as well which aren't associated with spectral lines but are important in the same sort of science. So probably in radio astronomy, one of the most important emission mechanisms, because so many sources we detect in the sky are seen through this, is synchrotron emission. So synchrotron emission is associated with the acceleration of an electron as it rotates. So an electron that's essentially in orbit through a magnetic field. That then, of course, there's an acceleration associated with that as it orbits, which leads to a change of direction, which leads to the emission of a photon. And this is a continuum emission process, and it's seen so often in radio sources because magnetic fields are prevalent in active galactic nuclei, radio, and also in star-forming regions. So you get the synchrotron emission associated with magnetic fields in those, and of course the plasma of electrons that are in that medium. And then, of course, we have as well something called free emission, which generates a thermal spectrum. So synchrotron emission doesn't generate a thermal spectrum; it generates a non-thermal power law spectrum. But free emission generates a thermal spectrum, and this is due to the interaction in a plasma between electrons and nuclei, which the electrostatic interaction there leads to an acceleration, essentially a change of direction of the charged particles, which then leads to the emission of a photon. And free emission is seen in many astrophysical contexts, particularly in the Milky Way galaxy. We see it in H2 regions associated with ionized gas in star-forming ionized hydrogen regions. In a radio astronomy context, here is an example of combining these different emission and absorption mechanisms. So here we have what's called H1 absorption. So specifically, this is 21 centimeter line absorption from neutral atomic hydrogen towards a background radio source. In this case, the radio source is actually emitting synchrotron emission. So we have what are called radio AGN, radiolab AGN. These are active galactic nuclei at the center of galaxies, and we have these radio emission from the plasma jets that are emitted by these active galactic nuclei. And so they emit a radio continuum in their spectrum through synchrotron emission. So it exhibits a classical sort of power spectrum of radio emission. And at specific frequencies, the foreground atomic hydrogen, H1, absorbs this background radio continuum, and we get an absorption line, which is what you see here in these spectra. So we're seeing here these H1 absorption lines. And you can see that what the authors have done in this particular work is they've shifted everything with reference to a rest velocity, a rest redshift. So the redshift of the object that they're studying. So what you're seeing now is the velocity with respect to the active galactic nucleus, right? So that's what you're seeing here. And so you can see the velocity of the H1, the foreground H1 gas, and you can see in this case that the majority seems to be blue shifted actually. So what you're seeing here is a lot of the gas seems to be moving towards us away from the AGN. Now that could be associated with just the ordinary rotation of gas in that galaxy, or it could be actually something to do with potentially to do with outflowing gas, although in this case I think that's probably not true. In this study this was probably just due to rotation of an H1 disk in front of the radiolab AGN. Okay, and so this is an example, an extragalactic study of neutral atomic hydrogen using absorption lines. And this is really important because this allows us to look at things like the interaction between an active galactic nucleus and the surrounding interstellar medium, the neutral interstellar medium in these galaxies. H1 absorption is also a very important technique in the Milky Way galaxy for resolving this problem of the kinematic distance ambiguity. Now, as I mentioned before, any object that we measure the velocity of that's within the solar circle, so has an orbit that's within 8 kiloparsecs of the galactic center, has this problem when we measure its velocity, its radial velocity with respect to us, we get two possible kinematic distances that we could infer from that measurement. So it can either be closer to us on the near side of what's called the tangent point, or on the far side, and that could be quite a large range of distances that it could be at. Now this is very important because if we want to, for example, know what the real distances, the physical distances of say an X-ray binary star system, we want to know then we want to know that in order to be able to measure its luminosity, which is very important. Likewise, we may want to, for example, map out regions of ionized hydrogen in the Milky Way, these what are called H2 regions, which are emitting radio wavelength radiation through free emission, which I've just discussed. And we want to map that out. We want to map these star-forming regions out in the Milky Way galaxy. And in order to be able to do that, we need to know what their radial distances are. So we need to be able to resolve this kinematic distance ambiguity. So this can be done through neutral hydrogen absorption. And the way it's done with hydrogen absorption is using the fact that, by definition, the absorbing gas has to be in front of the background source, right? So that has to be true, which means that if we observe hydrogen absorption that is at a velocity that is greater, the velocity is greater than the velocity of our object, this means that the object has to be greater than what's called the tangent point. So it has to be on the far side distance. But if the absorption is only seen at velocities less than the velocity of the object that we're looking at, then it means that the object has to be on the near side of the tangent point, and so it has to be nearer to us. And so that piece of information, the hydrogen absorption, tells us what the distance is. It resolves the kinematic distance ambiguity. And this is partly because the definition of absorption, but also partly because hydrogen is prevalent throughout our galaxy, particularly in the plane of our galaxy. And so it's just the fact that neutral hydrogen is such a hydrogen itself is such a common element, and the fact that there's so much neutral hydrogen gas throughout our galaxy that we can use this technique. So that's the end of the first part of this lecture, which focuses on some of the science that you can do with spectral lines and where they come from. Now, I emphasize the word some because, of course, there is a huge range of astrophysics that you can do with spectral line astronomy, and I've only really covered some of that and focused on some of the galactic and extragalactic applications that you can apply this to. Hi everyone. Okay, welcome to part 2 of Spectral Lines. This lecture is going to focus on more the aspects of the data reduction. So we've just talked about some of the science you can do with spectral lines. Now I'm going to highlight some of the important differences and considerations for observing spectral lines and data reduction and doing some of the analysis on the data. So let's move on with that then. So what does spectral line interferometry actually mean, and what are the key differences from, say, normal continuum interferometry? Well, if you think about it a little bit, it's not obvious, but really it's all about whether the flux density of the signal changes rapidly with frequency. So when we talk about continuum observations, we typically are thinking about the signal changing slightly with frequency, but not very rapidly. And so there's not a huge amount of information contained in the frequency dependency of the signal. But in spectral line interferometry, what we care about is how the signal changes with frequency and specifically where it may be located in frequency space. And so we often care about a third axis called the frequency or the velocity axis. And we'll get on to why those are synonymous in a minute. But we have here, for example, an example where we have a plot showing the flux density of a source as a function of the velocity axis or the frequency axis. And you can see that there appears to be a rapid increase around about close to 0 kilometers a second in velocity at the position of this source, which corresponds to actually carbon monoxide emission, the 6 to 5 J transition associated with a high redshift quasar using the plateau-de interferometer. And on the right hand side, you see here an image of this spectral line. So this actually shows that the channels. This is basically a composite image constructed from the channels where there's signal showing the position of this. At the position of this quasar, the CO emission. However, even though I said that the key difference, of course, is that with spectral line interferometry, we care about how the signal changes with frequency, and with continuum, we care less so. Actually, with new wideband correlators, we do tend to care a bit about the response of the telescope as a function of frequency. And in fact, you do need to worry about separating the response of the telescope as a function of frequency and the signal, the actual astrophysical signal as a function of frequency for continuum observations as well. This not only affects producing continuum images, but also you may want to actually understand how the continuum source behaves as a function of frequency as well. So even though this matters mostly to people who care about spectral line science, actually, for those of us who observe continuum sources, this is also a consideration. And so, when we look at our data, we want to look at how the telescope responds as a function of frequency as well as a function of time. Okay, so this lecture has been split into two halves. In the first half, I'm going to talk about how you set up your observations for spectral line work and the sort of considerations you may need to think about there. And then in the second half, I'm going to talk about how you reduce your data and analyze it in order to achieve the science that you want to achieve. Okay, so what sort of things do you need to think about when setting up your observations specifically for spectral line work? So with any observation, you want to first of all think about what your science case is. So what are your science goals? What spectral lines should you be choosing to be able to achieve those science goals? And of course, that's very important. And we've talked a little bit about some of the spectral line science you can do in the first lecture. Okay, so once you've got your science goals, then you may want to choose which source you want to observe or sample of sources in order to achieve those science goals. And you, of course, want to research around their properties. So once you've got your sample and you've got your science case, then you want to think about which facility you might use in order to carry out this experiment. And also, once you've got your facility, you might want to think about its configuration as well. So what are the correlator configurations? What are the spectral resolution, for example? What is the bandwidth? And also what the array configuration might be. So what is the spatial resolution you need to achieve your science? And once you've got all that, of course, you also want to think a little bit about the source velocity reference frame. And what that means is, of course, is that, does the facility have the ability to be able to observe the spectral line that you want to look at once it's been shifted away from its rest frame frequency based on either redshift or blue shift. And also, we're going to talk a little bit about Doppler tracking as well. Some facilities can actually, on the fly, track velocity shifts due to the relative motion of the Earth with respect to the source, and we can talk a little bit about that later. Of course, one of the other big considerations as well is, once you've decided on these things, what is the channel width that you want, and how many channels do you want across your spectral line? And that's really important, of course, because you want to probably resolve your spectral line in several channels. So how wide do you expect your spectral line to be in frequency, and that will then dictate what your channel width is. And in addition to that, you want to think a bit about the total bandwidth as well. So you obviously want your bandwidth to at least span the spectral line, the expected width of the spectral line, but you'll also want to maybe have some bandwidth either side of the spectral line. This is important for such considerations as continuum subtraction, but also you probably want to characterize the spectral baseline as well to see whether there's any residual variation due to the change in the response of the telescope as a function of frequency. And so once you've got all that, that's very specific to spectral line work. But of course, like any observation, you also want to choose your calibrators, and there are some other considerations there potentially for spectral line work, which we'll get onto. And finally, as well, this is quite important specifically for spectral line work, is that of course we're splitting the data up into multiple channels, into sometimes many thousands of channels, and this can make the data volumes much larger than what you get when you do continuum work, where you tend to average in frequency space. And so that can actually be a consideration. So data size and data rate are very important in spectral line work, because often you may want to analyze your data locally on your own machine or in your own home institution. And so that requires copying the data somehow from the observatory or where the data have been produced, been correlated. And so you need to think a little bit about that. Is it going to be feasible to both store and copy that data across to your home institution? I'm now going to go into a bit more detail about each of these steps. So as I mentioned, the first step really is to obviously define your science case and which lines you want to use to achieve that science case. And once you've got that, you then want to choose the telescope that you want that is sensitive in that band. So, for example, with the Atacama Large Millimeter Submillimeter Array, that's obviously a millimeter wavelength telescope that has receiver bands that are sensitive at those wavelengths, and there are specific spectral lines such as carbon monoxide and other molecules for which you can detect using that telescope. But it may be the case that you want to look at neutral hydrogen, for example, the 21 centimeter emission line of neutral hydrogen, in which case you're going to go to a much lower frequency telescope, such as the VLA or Meerkat in South Africa. And there are lots of obviously science cases that you can achieve with spectral lines. So spectral lines tell you a lot of things about galaxies. They can tell you about the kinematics of the galaxy, so the bulk rotation, for example, like in this VLA image of the H1 gas that is ubiquitous throughout this galaxy, and it gives you a really nice measurement of the sort of total, the global rotation of this galaxy and its dynamics. But you can also learn a lot about the physical properties of the gas in galaxies and in our own galaxy as well. You can learn about the chemistry from the different line ratios, the excitation temperature. You can even learn about the magnetic field strength, and also even on smaller scales, turbulent motion as well. So there are a lot of science cases for doing spectral line work. Right, so we can look at these different science cases in a bit more detail, and I'll just go through some of the more commonly observed spectral lines. So probably one of the most commonly observed spectral lines is as I mentioned, is a 21 centimeter line of neutral hydrogen. This is a really important transition in radio astronomy. It allows you to trace the neutral gas in galaxies out to large radii, and therefore using the shift in the line, you can actually determine the dynamics of the gas, the baryonic content of the galaxies, and that tells you something about the enclosed mass, of course, in the galaxy, and including its dark matter. So it's a very important diagnostic of the motion of a galaxy, the internal motions of a galaxy. In addition to that, it of course tells you about the abundance of atomic hydrogen in that galaxy. So it tells you about its column density, and you can also use it as a diagnostic for determining, particularly for the optically thick gas, for determining its temperature, through the absorption line. You can also use the dynamics to determine the baryonic Tully-Fisher relation, which also allows you to measure the Hubble constant. So not only that, it has quite important applications to cosmology as well. So this is a workhorse of spectral line, of radio astronomy spectral line work, and it's a very important transition. Another important line at radio wavelengths are radio recombination lines, particularly from hydrogen, helium, and carbon. So this now, rather than tracing the neutral gas, this is more focused on the ionized gas and its dynamics. It tells you a lot about the physical properties, such as the electron temperature and density. And it also tells you about things such as the abundance ratio of those elements in the gas. You can also it also, through Zeeman splitting, so through interaction of the transition with the magnetic field, you can actually start to measure the magnetic field strength by measuring multiple lines associated with a given transition through the Zeeman splitting mechanism. So these lines are very important for determining some of the physics of both in our galaxy and in other galaxies as well. And finally, of course, we have the molecular lines. So there's a whole plethora of molecular lines, of course, associated with the molecular gas. Again, these are very important. So the velocity that you infer from the line, so both from its broadening and its position, so how it's been shifted with respect to its rest frequency, tells you about the dynamics of that gas, that component of the gas in a galaxy, or in our own galaxy in a cloud, for example. And in addition to the dynamics, of course, you learn about the physics, so you learn about the temperature of the gas and its density. You can also learn about its magnetic field strength and and importantly as well, of course, the chemistry of the gas. So the abundances of the different molecules and the chemical properties of the molecular gas, the different elements that are present. So some of the more common molecular lines that we observe include carbon monoxide, which is an important tracer of molecular hydrogen and molecular clouds in galaxies. Also the hydroxyl radical, which tends to trace the more diffuse molecular component, as well as other important molecules such as water, silicon monoxide, hydrogen cyanide, and ammonia. And we should also mention that not only do you observe these in emission, but similar to the radio recombination lines and atomic hydrogen line, we can observe these in absorption typically against background continuum sources, as well as in masers where you have population inversion that are associated with star formation and also with AGN as well, with active galactic nuclei. So there are a lot of these lines are obviously very important for many different physical and chemical processes going on in galaxies. And so once you've chosen the spectral lines that you want to observe in order to carry out your science, you want to then think about, of course, the source or the sources in your sample where you'll be observing those spectral lines. And you want to obviously think about things such as where their position is in the sky, what their sizes are, what their velocity is with respect to us, which is very important because, of course, cosmological redshift for highly redshifted objects will shift any observed emission or absorption lines away from the expected frequency of that line in its rest frame to a much different observed frequency. And so you need to think a little bit about what the velocity of that object might be with respect to us in order to choose the right sample that may all have the same velocities. The other thing you might want to think about as well is the estimated brightness of your emission line, or indeed a background continuum source where you want to detect an absorption line. Those are important considerations as well, because it might just be far too faint to be able to be feasibly observed. So, for example, the atomic H1 21 centimeter line, it becomes very difficult to observe that beyond nearby galaxies. So you'll need a considerable amount of integration time to detect the H1 line beyond redshifts of about 0.1. So you want to obviously research the literature to be able to find your sources for your sample. Obviously, there's a lot of great online literature now resources to be able to do this. So the commonly used ones, of course, are things such as NASA's Astrophysics Data System, the Abstract Surface, so ADS, where a lot of the literature you can find is, as well as things such as NASA's Extragalactic Database, which has a lot of information particularly about extragalactic sources as well, extragalactic galaxies, and likewise you can use CDS as well, and various other online resources which are important. And so once you've got your sample of sources and the emission lines that you've chosen to observe, you want to choose the facility that you want to use to observe those with. And so there are a lot of facilities out there now available that you can apply for time on. And here's just a list of some of them. And some of them are more appropriate for the sorts of spectral lines that you may want to observe than others. So for example, if I wanted to look at the 21 centimetre line of neutral hydrogen, I might apply for time on the Very Large Array or the Australia Telescope Compact Array. If I want spatial resolution, then I may even look for time on, for example, the European VLBI network. But if I'm more interested in, say, molecular lines, I may decide, particularly at high frequencies, I may decide to apply for time on ALMA, the Atacama Large Millimeter Submillimeter Array, or the Plateau de Boer Interferometer. Sometimes the at lower frequencies, the Murchison Wide Field Array and LOFAR, they tend to focus on the epoch of reionization science case. So that's the 21 centimeter line at very high redshifts, above redshift 6, where they're looking for the 21 centimeter signal associated with the ionization of neutral hydrogen in the distant past, in the dark ages of the universe. However, some spectral line work has been carried out for molecules in our Milky Way galaxy with the MWA, as well as carbon recombination lines as well. There has been some work there with LOFAR and MWA. So obviously, to get information about the sort of telescope that you should be using, what you want to do is you want to use, again, the online resources available to you. So, these facilities have a lot of good web pages where you can learn a lot about each individual telescope to understand whether it's suitable for your proposed observations. So obviously, when you're thinking about that, you want to think about not only whether the telescope can observe at that particular frequency for the spectral line that you're interested in observing, but also you want to think about the array configuration as well. And so, the VLA and ALMA, for example, can observe in different array configurations, and when you propose for particular configuration. Why do you care about that with spectral line work? Well, for example, if you're looking at absorption lines where you're detecting an absorption line against a compact, small, bright background radio source or millimeter continuum source, you may want to consider higher spatial resolution to be able to interpret the spatial distribution of the absorption that you detect against the background radio source. Likewise, you may want a smaller array for emission line work, particularly if you want to detect extended or faint emission, where you want basically better surface brightness sensitivity. So the array configuration is an important consideration when you propose your observations. So a really important subtlety of spectral line work is choosing the right standard of rest or velocity reference frame with which you're going to measure the velocities of your spectral lines with respect to. Now, what you choose sort of depends on the field of research that you're working in. This is, of course, important because, of course, motion is relative. And so the sun spins about, the Earth spins about its axis. That causes a diurnal variation, so a daily variation of about 0.5 kilometers a second in amplitude. It also, of course, orbits the sun, so can shift by up to 30 kilometers a second in any given direction in the sky over the year. And of course, the sun is in motion in its local area, as well as the Milky Way being in rotation, as well as the Milky Way itself moving in the local group. And so there's all this relative motion going on. And so we need to adopt a reference frame with which we then define velocities of spectral lines with respect to, or redshifts indeed. And so which standard of rest you choose depends really on the field of research that you're working in. So for people who are interested in the Milky Way, they will often use the local standard of rest. So this is a local standard near to the sun in the Milky Way that is adopted as sort of the reference frame with which all velocities of other parts of the Milky Way are measured with respect to. For extragalactic work, people tend to use the heliocenter or the solar system barycenter, which is just the center of mass or center of motion of momentum with respect to the solar system, and that's often adopted for extragalactic work. Now, the way in which you define velocity can depend on certain conventions that you use. Now, for most extragalactic work, as I said, that the reference frame or the standard rest that's used is the heliocentric frame. So we correct from the topocentric to the heliocentric. Then people might choose to quote a recessional velocity, for example, for a galaxy that is moving away from us due to the Hubble flow, or they may quote a redshift. Now, when people quote velocities, velocity associated with a redshift or a blue shift there is a full relativistic expression for that, but often a convention is used to define velocity, which is an approximation to that correct relativistic shift, velocity shift, recessional velocity. Now, in radio astronomy, there's a convention which is given by this equation. So that on the left-hand side there, you have v radio divided by the speed of light, and on the right-hand side, you have the rest frequency nu naught, subtracting the observed frequency nu divided by the rest frequency nu naught. And this is the radio convention defining recessional velocity. I should mention, though, that there is an optical definition, which is effectively the inverse of this, using wavelengths that is slightly different. And the reason why this convention is adopted in radio astronomy is because if you now take a difference, so if you take the differential of that equation, then you notice that changes in frequency are proportional, or changes in velocity in this definition are proportional to changes in frequency. And so that's why this convention is adopted. And likewise, in optical astronomy, changes in velocity in that convention are proportional to changes in wavelength. And so when you're matching channel widths, channels and widths, bandwidths to velocity, that's why this convention is adopted. I should also mention, though, that the International Astronomical Union have adopted the optical convention for recessional velocities, not the radio one. So you're discouraged to in publications now to use the radio convention, although this is used a lot in discourse, scientific discourse in radio astronomy, as well as in proposals. Now, as I've mentioned, the Earth, obviously, when it's spinning on its axis, causes a shift by up to 0.5 kilometers a second in velocity with respect to a given source in a given direction. And so if your telescope is observing at a fixed sky frequency, then the spectral line that you're observing is going to shift around by plus or minus 0.5 kilometers a second throughout a 12-hour track, throughout an observation. And so you may not want that to happen, because particularly if you're observing at high spectral resolution, where your channels are, or your line is narrow compared to 0.5 kilometers a second, you're going to see a significant fractional broadening of your line as it shifts around, if you were then to average over that observation without thinking about this shift. So you can either try and correct for it after the fact in data reduction by interpolating or binning to fixed velocities, or you can, some observatories allow you to Doppler track, where the sky frequency is changed throughout the observation to track, to follow that shift. And so there are these two different options that you may want to consider. And it really depends on whether that effect is a very important effect for the observation that you're carrying out. The next step in setting up your observations is to think a little bit about the number of channels you want across your spectral line, the total bandwidth that you have available, and of course, the channel width. So typically you're going to want several channels across your line to resolve it. So, you may want to consider having at least five channels across your line. It depends, of course, on whether you're interested in measuring the kinematics and whether whether your emission is spatially resolved. So, whether you're, for example, with the H1 line, whether you want to sample just the integrated line over the whole galaxy, or whether you want to resolve individual velocity components and get a measurement of the velocity dispersion. As I've mentioned before, when you consider the total bandwidth and the number, and also the spectral resolution, you want to think a bit about whether you've got enough line-free channels either side of the spectral line. And this is important because when you come to subtract the continuum later in data processing, you need enough line-free channels to get a good fit to the continuum to remove it from your data. So that's an important consideration. The other thing you want to think about as well is that you may find that not so much for interferometers, but sometimes for single dish telescopes, you may get a significant bandpass ripple. You may get a significant spectral bit ripple in your baseline, which you may want to characterize and subtract out. And so sometimes having line-free channels either side of your spectral line is important for doing that. Right, so if you know the velocity coverage that you want to achieve for a given observation, so say you've got a spectral line and you're measuring the dynamics of the gas and you want to have a reasonable velocity coverage, then once you've got that, you need to determine what the frequency bandwidth is that you need in order to be able to get that velocity coverage for that spectral line. And so we use this equation here, which basically relates the range of observed frequency that you need at a given frequency to cover a given velocity. So what we want to calculate is delta F, and we know what delta V is, and we know what the observed frequency is F for a given spectral line. And so, for example, if we're observing, say, the water line, the H2O line at 22 gigahertz, and we want velocity coverage of 100 kilometers a second, then we're going to need to have a bandwidth of at least 7.4 megahertz. But as I've already mentioned, you're going to need some gaps either side of that, maybe. Plus, you need to take into account that you're going to want to consider that the sensitivity might drop off at the edges of your band due to the filter, and so you want to make sure that you've maybe got a bit of extra space either side. So you may want to round that up a little bit. And so once you've determined the bandwidth that you want for the observation, you're also going to want to think about the spectral resolution of the observation as well. So how many channels, what the width of your channels are. And so you want about at least 3 channels across a spectral line, both to be confident of the detection if it's a detection experiment, but also to correctly characterize its width. And 3 channels are, just sufficient to do that. You may want more channels across the line as well. And of course, going to higher spectral resolution isn't necessarily a bad thing, because you can always bin after the fact in velocity and to recover signal to noise. So don't be worried to go to higher spectral resolution because you can always recover signal to noise. Of course, you can't improve your spectral resolution after the fact, after the observation, but you can reduce the spectral resolution after the fact to get signal to noise. So for example, if we have a line, say 1 kilometer a second, at 20 gigahertz, then we're going to want a spectral resolution of about 25 kilohertz, using the same equation that we used to calculate the bandwidth earlier in the previous slide. So typically, a correlator will have a sort of maximum bandwidth or number of channels for the required velocity resolution. So often you'll choose the velocity resolution and then you'll just try and choose the maximum bandwidth associated with that. And that's typically what happens when people set their observations. Now, for some spectral line observations and correlators, an issue can be what's called Gibbs ringing. And this is to do with the way in which the channels are constructed. And so you get this effect where you get some ringing of a given spectral channel into adjacent channels. And now, if you're observing a very strong line, or you're observing a frequency where there's a significant amount of strong radio frequency interference, then this is going to be imprinted on that signal, and you're going to get this additional behavior in the spectral line. Or leakage from the RFI into the channels where you're observing your spectral line. And so to get rid of this, you can Hanning smooth, but that will end up, so Hanning smooth effectively reduces your resolution by at least a factor of 2, your spectral resolution by a factor of 2. And so you need to take that into consideration. So for example, when you observe with the Atacama Large Millimeter Array, ALMA, your channel width is your channel width is typically your spectral resolution for a given channel width is typically twice the channel width, channel separation, and so that does need to be taken into account when you're setting up the observation. And now, once you've got the frequency setup that you need, so the spectral resolution, importantly, and the bandwidth, then you're going to need to think about the sensitivity. So how long are you going to need to observe? The integration time you're going to need to get a detection for a given spectral line, to get a detection in the channels, in each of those channels. So for a continuum observation, you think about the total bandwidth and the signal to noise in that bandwidth. But for spectral line, the bandwidth that's relevant is now the channel width. And so you need to think about what is the strength of your spectral line in a single channel, and what is the noise for a given integration time that facility is going to give you. And are you going to have at least 3 or 5 sigma in that channel, in a single channel, to be able to detect the signal in that channel? And so this is a very important consideration. Of course, that means that it's a lot harder to detect spectral lines, particularly emission lines, than continuum sources for that reason. The next step in your observing setup is to choose the calibrators that you want to use for your observations. And of course, what's very important in spectral line work is the bandpass. Now, the bandpass is the response of the telescope as a function of frequency. So you've talked about calibration in this course associated with phase and amplitude of the gains, the antenna gains, as a function of time, and to calibrate that response out. But these are also functions of, the gain is also a function of frequency as well. So the response of the telescope to signal is a function of frequency. And so that also needs to be calibrated out. And so we need to choose a calibrator to correct for that. And of course, characterizing and correcting the bandpass response of the telescope is very important for spectral line work. So if you haven't corrected out any behavior in amplitude, that could easily mimic a spectral line, emission or absorption line, particularly when you have weak lines against very bright continuum sources, which may amplify any bandpass response of the telescope and imprint on your data with something that looks like an emission or absorption line, or completely confuses the signal and you can't actually work out whether you've got an emission or absorption line there. Likewise, in phase, if you haven't corrected out the phase of the bandpass properly, then you're going to if you care about, for example, the position velocity of the spectral line, then a phase error is going to make it artificially move it around, so as a function of frequency, and so you may infer Doppler motion that isn't actually there. So when you care about, for example, measuring the velocity of gas, that could be quite important. And of course, this has similar implications for pseudo-continuum, where you also care about the spectral behavior of a continuum source as well. Bandpass calibration is therefore clearly very important. So how do we actually choose a good bandpass calibrator? What makes a good bandpass calibrator source? Well, of course, what you want to choose is a source that's very, very bright, that has high signal to noise, and you want it to have sort of as few spectral features as possible. So you want it to have a reasonably flat continuum spectrum, which is also absent of any spectral lines at the frequencies you're observing. So you don't want an absorption line, for example, in this continuum source's spectrum at the frequency of the line that you're trying to detect. The other thing that you want to, as I mentioned, you want high signal to noise, and in particular, you want the signal to noise ratio on your bandpass calibration source to be much greater than the signal to noise ratio on the target. And that's because when you do the bandpass calibration, what you're doing is you're transferring solutions that have been determined as a function of frequency. So gain solutions that have been determined as a function of frequency from the bandpass calibrator source to the target source. And in doing so, you're transferring any noise that's in that in those calibration solutions to your target spectrum. And so you want that to be as small as possible relative to the target spectrum. And so you want to choose a source that is significantly brighter, maybe a factor of 10 or more brighter than any emission line or a continuum source where you're detecting when you're trying to detect absorption lines. Now you could do that if you're doing if you're trying to correct on a channel by channel basis the bandpass. That's what you would do. You can also, if you assume that the bandpass is sufficiently smooth, you can actually smooth the bandpass by either smoothing it or fitting a polynomial to it to try and recover signal to noise in the bandpass if you're concerned about the signal to noise being an issue. So your bandpass calibration source is very important because that calibrates out the bandpass response to the telescope, and that's clearly one of the most important calibrations you need to do for spectral line work. But of course, like any observation, you're going to want to also calibrate the flux scale to actually get an accurate measurement of the strength, the intrinsic strength of the emission line. And that's particularly important for emission lines. Absorption lines, less so, because of course you're there measuring a fractional absorption for background source, and so it's less important, but still something you might want to do, particularly if you're interested in the flux densities of the continuum sources that you're looking for absorption against. And so one of the things you might want to be careful about when you're doing high spectral resolution observing and choosing a flux calibration source is just to be careful that your flux calibrator could have a lot of spectral structure in its spectrum. And be careful when you do the flux calibration that you mask out those channels when calculating what in data reduction, when you're calculating what the correction factor should be to scale to transfer your gains to the right flux density scale. So that's just a consideration for spectral line work when you're doing flux calibration. And the final consideration, which is not so obvious, that I mentioned at the beginning, is that you want to consider whether what your data rates are going to be for this observation. So if you imagine that, you could have up to thousands of spectral line channels with modern correlators. And so the amount of data, the data volume could be considerably greater than a standard continuum observation where you're averaging in frequency. So when you're looking at high spectral resolution or indeed high time resolution or with multiple polarization channels, you do need to worry that your data rates may be very large. And so the data rates depend on all these different factors. And so often now when you make a proposal for an observation with a modern telescope, such as the VLA or ALMA, it'll tell you what your data rates are going to be. And sometimes these observatories have a cap on that. Obviously, your data sets can be in the many hundreds of gigabytes. And not only are there restrictions on the amount of data that you can generate, but also you're going to have to think, well, how are you going to process that data? So the data are going to be at the observatory or at a regional data processing center, but then you're going to need to be able to download those data and copy them across to your location where you're going to do the data analysis. And so you need to think a little bit about that. Perhaps you can, one of the considerations, of course, is perhaps you can reduce the spectral resolution to your needs or the time averaging as well. And you need to think a little bit about that when you're setting up the observation. Okay, so we've set up our observations, we've actually now carried out our observations, and we've got our data. We've downloaded our data and we're ready to reduce it and process it. So now I'm going to talk about some of the steps required to do that. So the first step, of course, you're going to want to do is to look at your data and see whether there are any parts of the data that should be excluded, excised, due to, for example, radio frequency interference or possibly glitches in the hardware, such as in the correlator, which render parts of the band unusable and potentially could corrupt your data as you reduce it. So there are a number of ways of looking at the data. You don't want to look at it in a channel-by-channel basis, as typically with modern correlators there are far too many channels. That'd be an inefficient way of looking at your data. But what you would normally do is look at, say, plots for a sort of array with a small number of antennas. You may just look at the baselines and look at the spectra, the cross-correlation spectra for each baseline, antenna baseline, and look for any evidence of strong radio frequency interference or glitches in the data, which you can then exclude those channels. Automatic flagging routines do exist. You have to be careful with these. So for weak lines, they're not really going to flag anything that's sort of a weak extragalactic line, for example. However, you do have to be a little bit careful with these sorts of flaggers, particularly for strong lines that might be detected in individual visibility spectra. You've got to be a bit careful that they don't get flagged by these routines. So typically, it's a good idea to obviously flag as much as possible your calibrator data. So for your bandpass calibrator, you may flag the channel ranges that are affected by RFI, but then smooth across or fit across the bandpass solutions over the affected regions. But you may consider only flagging the calibrator sources to get good calibration solutions, but then not necessarily flagging your target field until later, if at all, depending on whether it's for example, the radio frequency interference is time dependent or not. So it's not necessarily a good idea to flag your target data straight away, because it doesn't really affect the calibration solutions until maybe you come to do things like self-calibration. And after you've done your flagging, you'll want to do the bandpass calibration step. So you've got your bandpass calibrator, and you're going to run a bandpass calibration task in Casa or Myriad or APES, any of these reduction packages that will solve for the gain response as a function of frequency. And so how do you know when that's gone well? Well, what you'll do is you'll look at the bandpass solutions for antenna baseline, for a pair of antennas, and the solutions in phase and amplitude should look something like this. So the solutions should be reasonably smooth. You're basically reproducing the bandpass response of the telescope, and it should be smooth, so they're not dominated by noise. There should have been enough signal to noise on your calibrator to get a nice nice solution like this. Another way of looking at whether the calibration's worked is you can look at what the calibration looks like for a bright point source. What the phase and amplitude looks like for a bright point source before and after bandpass calibration. So beforehand, you should see some variation in phase and amplitude as a function of frequency due to the bandpass response of the telescope. And then in after bandpass calibration, so once it's been calibrated, these variations in frequency have been calibrated out. They should look pretty flat. So phase should be about 0, of course, for a point source at the phase center, and the amplitude should be pretty flat as a function of frequency, as you can see here. And here we have some examples of sort of bad bandpass solutions which you may want to try fixing. So perhaps there's something's gone wrong. Maybe this wasn't the right source to observe. Maybe you need to, if the noise level's too high in the solutions, you may want to consider just fitting that out using some sort of polynomial fit to the bandpass solutions or smoothing them. It depends really what the problem is here. Maybe there was one bad antenna which is corrupting the calibration solutions for everything else. So you need to go back through and have a look at the data to see what's going on. So after you've done bandpass calibration, you're going to probably perform a couple of other calibration steps, including calibrating the flux scale using a primary calibrator, and also doing a phase reference calibration using a source near to your target field. And so what you do is you transfer the bandpass calibration solutions to those objects and then calibrate on those objects before then transferring all the solutions to your target field. And once you've finished doing calibration, you're going to also want to think about the spectral line itself. And one of the things you need to consider is the Doppler correction. So as I've mentioned before in this talk, you need to think about the reference frame that you're considering. And so, for example, if you want to correct to the heliocentric frame, so that's the reference frame for velocities measured with respect to the sun, then there's going to be a correction of up to 30 kilometers a second between the observatory's frame, the topocentric frame, to the heliocentric frame. But there's also this additional correction due to the spin of the Earth about its axis, this half of a kilometer a second. Now, for a single observation, one heliocentric correction is going to be fine, but this diurnal variation due to the Earth's rotation about its axis, obviously the line is going to shift significantly due to that within an observation, particularly obviously if your spectral resolution is similar to this half a kilometer a second shift. And so there are a number of ways of dealing with this. So there are tasks within CASA and APES and Myriad in these data reduction packages that can deal with that. And so what it will do is it will make the calculation required to map a given time and frequency to the correct velocity in that reference frame for your spectral line. And so when you come to plot to construct your cube, for example, if you construct your cube at a fixed velocity, then it's going to correctly put the data into the right velocity bin for that frequency channel. So an important aspect of spectral line data reduction is what's called continuum subtraction. So when you observe a field, obviously you're going to have your spectral line, your emission or your absorption line, and you're going to have a lot of continuum emission in there as well. And this continuum emission is going to limit your ability to be able to reach the spectral dynamic range that you need to do your science. And it's going to complicate the analysis of the line. And so what you're going to want to do is subtract that continuum out of the data when you go on to then image your spectral line. So the important steps involved in continuum subtraction, probably the most important part of that is to identify the channels that don't contain the spectral line. And that allows you then to characterize the continuum, model it, and remove it from the data. And in detail, there are two approaches to doing this. So the first way of doing this would be to subtract the continuum in the UV plane in the visibilities. And so there are a number of ways of doing that. You can either fit using a task called UV-lin or UV-cont-sub in CASA, which is where basically each visibility spectrum is fitted by a polynomial of an order defined by the user. So it just fits the visibility spectra and subtracts that out. And when you're doing that, what you're going to want to do is you're going to want to identify and tell the program the channels that contain the line signal so that they're ignored in that fit. And then it subtracts out the polynomial and you're left with a visibility data set that is free of the continuum. Another way of subtracting out continuum in the UV plane in the visibilities is to subtract out the continuum model that is constructed during clean. So if you run a continuum clean and construct a continuum model, then you can subtract that from the visibility data as a first step. And that often works very well. And then you follow up with a UV lin step that subtracts out the residual continuum emission as a polynomial. You can also do this in the image plane, of course, as well. So what you can do is you can form your cubes, your spectral line data cubes, and then fit each pixel spectrum and subtract out the continuum that way. And that's another way of doing things. And there are pros and cons to both. And no single method is really appropriate for a given situation. It's often the case, in fact, that you want to combine methods to produce a really nice continuum-free data set. In the same way that we use self-calibration to improve the quality of continuum data, we can do the same thing with spectral line as well. So if you have and you just of course need the signal, the flux density in your field to be able to do that. So if you have a strong spectral line, then you can clean and self-cal on that spectral line directly. Or if you have a weak line but you have a lot of strong continuum emission in your field, you can use the continuum image to self-cal on and then transfer those self-cal solutions across to the spectral line data and then image the spectral line data from there to form a cube where you've now got better calibration solutions from using the continuum. And likewise, when you come to image your spectral line data, it's analogous to when you do continuum imaging. So it's just, again, doing a two-dimensional inverse Fourier transform, but this time in making several images in channels as a function of frequency. So it's very similar, but of course there are subtleties associated with that. So the first thing, of course, is you've got a much larger data set, so it's going to take longer to clean, it's going to take longer to image, generally just takes a much longer time than it would with a single continuum image. The other thing you've got to worry about as well, of course, is particularly if you're mapping emission that changes its position with frequency, then you're going to want to, when you clean, to make sure that your clean region that you're choosing encompasses the emission and maybe the mask is a function of frequency as well. For example, as well, if you're cleaning absorption lines, then maybe what you would use is the continuum sources, boxes around the known bright continuum sources as a clean mask. The other thing you might need to consider as well is the robustness weighting that you apply when you invert and construct the image, the cube. And so, if you have faint lines, of course, the optimum there for returning signal to noise would be using a natural weighting, but it means, of course, you potentially lose spectral resolution. And so you're going to want to fine-tune the robustness parameters for the data that you have, for the array that you've used, to try and identify the right balance in signal to noise so that you recover signal, but also get the resolution to study the kinematics, the kinematic information that you get from the spectral line. After all that data reduction, what you're left with is a three-dimensional cube where you've got the image and then you've got a third axis, which is either your frequency or your velocity, the spectral axis. And so what you're going to want to do, those cubes can be quite difficult to visualize and to carry out scientific analysis. So now we're going to carry out some spectral analysis to be able to pull out the information that we want from that data cube. And so there's a number of ways of doing this. You can produce line profiles, which is basically taking a one-dimensional spectrum along the velocity axis, either at a particular position or over the whole image, averaging over the whole image to produce a single average spectrum. We might want to take channel maps, which is basically slicing images out for each channel. And you can also construct what are called moment maps, which is producing images that sort of collapse down the velocity information and allow you to be able to take moments of the velocity distribution in order to be able to analyze the kinematics of the gas that you're observing with the spectral line. And of course, there are other diagnostics such as position velocity plots, and also you can produce movies as well. And those are becoming more commonplace as journals and papers are going online, and you're able to publish these movies along with your scientific results. Here we have an example of some one-dimensional spectra extracted from the cube at different positions. So what we've done is we've extracted the spectra at given positions within the cube, and then we've plotted them on top of each other. And you can see that you get some information here about how the gas, in this case is carbon monoxide gas in this molecular cloud G305, and you can see how the gas is distributed in terms of its velocity at different positions within the cloud and within the cube. Now, to make a plot like this, so data reduction packages like CASA and APES do have functionality for plotting spectra, but often it's the case that what you want to do is something that you want to do something more flexible, more complicated than what's available to you, and often it's easier to export the spectra either in FITS or ASCII format, and then use Python or some other programming language, matplotlib, to be able to produce the spectra in the way that you want them for publication, and that's often what people do. Instead of plotting the one-dimensional spectra, we can take slices through the cube. So these now are images of the emission at for different channels. And so you can see here that as we're stepping through each of these panels, we're seeing an image of a different channel. And you can see that the emission increases at stronger frequencies that correspond to those peaks we saw in the spectrum. And while we can slice the data up, as I've shown, into one-dimensional spectra or two-dimensional images of each channel, the channel maps, sometimes you want diagnostics that more easily tell you about the velocity kinematics going on in the object that you're looking at. And the best way of doing that is to look at what are called the moment maps. So these are basically ways in which you can combine the information contained into the channels into a single map that tell you something about the moments of the velocity distribution. So moment 0 is just the total intensity. That's just the integrated flux density or flux in the line multiplied by the width of that line. And then we have moment 1, which tells you more about the sort of bulk motion. That's the intensity weighted velocity. It tells you about the bulk motion of the emission that you're seeing. So that's, or absorption, of course. And so that's often used for looking at, say, ordered rotation in galaxies. And then finally, another common moment that's used is moment 2, and this is the intensity weighted velocity dispersion. So that tells you about how much dispersion there is at a given position in velocity, and that tells you about things like the turbulent motion and just the unordered motion at that position. So here we have examples of the moment 0, moment 1, and moment 2 maps for these data. And so you can see that, so there are a couple of things to notice here. So if you think about what we're doing, we're basically summing over multiple planes. And one of the things we have to be very careful about is when we do that sum, is we're lending equal weight to each channel, the image in each channel. And so we have to be careful not to include channels that basically contain no emission, that there's no signal to noise there. And so what we need to do is we need to apply a clip which makes sure that we only include data that contains signal to noise, so that we don't artificially increase the noise in our final moment map. And so that's what we're seeing here. And what we also notice as well is that as we progressively go from moment 0 to moment 2, you notice that the region that isn't clipped gets smaller, and that's because the moment 2 map tends to be noisier than the moment 0 map, and so the clip has to be more conservative, and so that's what we're doing here. And the final diagnostic in your toolkit is the position velocity diagram. And this is just another slice through the cube. What you're doing is you're basically taking one axis through the image along a preferred direction, and the other axis is in the velocity in the spectral direction. And this tells you how the velocity of the emission or absorption that you're studying changes with position along that axis. And there could be a particular axis that you're interested in. For example, the major or minor axes of a galaxy, how the velocity changes with that. Or possibly, for example, the axis defined by a radio galaxy, the Jetster radio galaxy. You might want to look at how the emission from a certain atom or molecule changes along that. And it's a useful way of visualizing velocity structures in the object that you're studying. Okay, so this is the end of this second part of the lecture on spectral line science and data reduction. I hope you've enjoyed it, and I hope you enjoy the rest of your course, and thank you very much.